introduction now, okay? So Professor Anna Maria has received her graduate and postgraduate education at the Faculty of Pharmacy and Medical Biochemistry at the Zagreb University, where she currently holds a professor position at the Department of Medical Biochemistry. Currently, Professor Anna Maria is employed at the Clinical Hospital Simundic in Zagreb, where she holds the position of the Head of Department of the Medical Laboratory Diagnostics. She was the President of the Croatian Society of Medical Biochemistry and Laboratory Medicine from 2012 to 2018. Until the end of 2017, she has served as the Editor-in-Chief of the journal Biochemica Medica, published by the Croatian Society of Medical Biochemistry and Laboratory Medicine. She now holds a senior editor position in that journal. During her professional career, Professor Anna Maria has served the European Federation of Clinical Chemistry and Laboratory Medicine in various roles over the years as Executive Board Secretary from 2011 to 2017 and President-elect from 2018 to 2019. She now holds the position of the President of the EFLM from 2020 to 2021. She's been chairing the working group for pre-analytical phase since 2012 to 2018, and she currently acts as the expert consultant in this group. She was awarded the Best Young Scientist Award in 2000 and the Best Research Award in 2011 by the Croatian Society of Medical Biochemistry and Laboratory Medicine, with the Holtov Peterson Award in 2012 by the Slovak Society of Laboratory Medicine, and with the honorary membership of the Hungarian Society for Laboratory Medicine in 2012. In 2015, she was among the top 100 power list of the British Journal, The Pathologist. Professor Anna Maria has authored or co-authored numerous peer-reviewed manuscripts, and her research activities focus on quality management and the pre-analytical phase. Now, there's an act to follow, Anna Maria. The stage is yours. Thank you very much.
Thank you very much. Let me share my screen. Okay, can you see my screen? Anne, can you please confirm that you see my screen? Yes? Okay. Well, thank you very much for your kind introduction. The topic of my talk will be an update on sample stability. I wish to thank the organizers for inviting me. This is my second time in Dublin. The first time was during the face-to-face meeting, during the inaugural Palm Study Day. And this is my second time, but unfortunately virtual. And I hope that very soon in the future that the opportunity will arise again for us to meet in person, and for me to come back to a beautiful country and the wonderful city of Dublin. I will talk about today about stability, and I'll try to briefly address during the next 20 or so minutes why do I believe that stability is an issue. Why should we be concerned about stability? I will briefly mention the issues about the quality of stability data. I will talk about the problems with stability studies and how are they designed and how are they reported, and I will share with you what has EFLM Working Group for Pre-Analytical Phase done to address some of these issues. You know, if we would define stability, then stability would be the ability of a sample to retain the initial value of its constituents within specified limits over a period of time. And here comes the catch-22, under specified storage conditions. And those conditions are not only temperature, but also the exposure of the sample to light, the type of the blood collection tube, the sample type, the type of tube additive, the anticoagulants, whether the sample has been stored as a primary sample or an aliquot, whether the serum or plasma has been in contact with cells, and how long was it in contact with cells, when the sample has been separated from cells, what is the sample volume, really even the sample volume matters, the contact with air, etc., etc. So there are really a number of storage conditions and factors that may affect the stability of an analyte, and we have to make sure to think about all those issues and consider all those issues when thinking about the stability of our analytes. So to ensure that only samples of sufficient quality are analyzed, stability in a variety of different storage and transport conditions and specimen matrices should be known for each analyte. So we should know that for each analyte that we analyze in our laboratories. And this is, of course, a common sense requirement, but also it's a requirement by the ISO 15189, which is a standard for medical laboratories. And ISO clearly requires that laboratories have criteria for acceptance, and that sample stability is one of those criteria. When we think about, whether to accept or reject a sample, sample stability should be one of the key issues that should be considered when making such a decision. Now, when making such a decision, there are a lot of challenges, and in the rest of my talk, I will be talking about those challenges. And one, first and the foremost, is the evidence. You would really like to make that decision based on good evidence. So it should be actually an informed decision. However, unfortunately, the evidence that we have to support our decisions that we make in our everyday routine is missing and is very unreliable. And I'm going to share with you a couple of examples to illustrate what I mean by that. And another challenge that we have to face is the quality of the stability studies and the quality of data that they produce. At the moment, the quality is really not optimal. So there is a need to improve the way those stability studies are designed and the way that those stability studies are reported. Okay, let's talk about the evidence. I'm not going to talk about manufacturers in particular. I will not mention manufacturer names because this problem does not relate to one particular manufacturer. This problem is really related to all manufacturers in general. So this is one declaration, one claim that's one manufacturer A, for example, gives you for one of the major manufacturers, gives you for creatinine, stability of creatinine in serum and in urine. And they tell you that, serum creatinine is stable for so-and-so days at 2 to 8 Celsius and indefinitely when frozen. And the same for urine. Now, the problem with this is that very often manufacturers do not provide appropriate references for those claims. So if you look at the references that manufacturers have provided for these very important claims that we use in our everyday work to decide, to make decisions about our samples, those references are actually, one of them is a textbook and the other one is a manual. So the problem with those references is that these are not original studies. So these are not original data. If you go and look up this, the reference number 7, the WHO manual, this is you can find it on the WHO website. You can freely download it. And in this document, it says that the document is a summary of the findings published in the literature. So it's not an original study. It's a summary of many findings of many publications. And those publications have been done, some of them long time ago. This publication has been published almost 20 years ago. And the declaration, the manufacturer declaration, is very accurate. It's from the reagent in use. And those original publications that were basis for this manual have used methods that are, some of them very outdated and not in use anymore, and on instruments which are not in use anymore. If you look up the data for creatinine stability, so in this WHO manual, they provide data for creatinine stability in serum and the different types of plasma, and they provide 3 references for this stability. Now, if you look at those 3 references, one of them is for hematology measurements. We are talking about creatinine. And the other one is for measurement of leptin and leptin binding in human circulation. If you look up the data for creatinine, stability of creatinine in urine, again, you have 2 references, out of which one is about variations in lipid and apolipoprotein measurements. We are talking about creatinine, right? And the other one is a textbook, TITS. So to summarize, the problem with these claims is that they are not evidence-based. We don't have, the manufacturers do not provide evidence which they have used as a basis for these claims. And we are, let me remind you, we are using these claims to make some very important decisions in our everyday work. Another example, manufacturer B for troponin, very important analyte. This is this manufacturer recommends that the samples should be stored tightly stoppered at room temperature for no longer than 2 hours. Very important claim. However, the evidence again behind this claim are these three citations, out of which the first one and the third one are CLSI standards for handling and processing of blood specimens and for collection of blood specimens by manufacturer. And the second one is actually an FDA recommendation on what laboratorians should know to manage elevated results. So again, there is no evidence. The claim is not really supported by original data produced either by the manufacturer or by some other authors. And the last, but maybe the most awful example is the one where we don't have the evidence at all. So there are, I'm not going to name the manufacturer, but this is a manufacturer C, and this is a claim where you have, specifications that samples should be stored at 2 to 8 for 24 hours, and for longer storage periods, the sample could be frozen to -20. However, the manufacturer has not provided any reference for the evidence. So we have to just believe it. And the one thing that maybe is not associated directly with the evidence, but I would also like to draw your attention to the fact that those claims or declarations are very often very vague and not very detailed and not too specific. Like, for example, this one, which relates to the stability during the freezing. So the manufacturer tells you that you can freeze it for longer storage period. Now the question is how long? How long is long? Is it 1 month? Is it 5 months? Is it 1 year? Is it 10 years? Nobody knows. So this is this is not a very useful claim or not a very useful recommendation for us. So to summarize, what I've been talking about manufacturers' claims, I think there is room for improvement here. And the most often problems and issues related to those claims are that they are not based on their own studies. So claims are not based on manufacturers' data. They're not sometimes or very often even based on original studies. They're not supported very often by any reference. And those data are quite often outdated. They're based on some old methods which are not anymore in use. So obviously we need, there is a room for improvement, and we need better stability data. So when we think about producing better stability data, then we have to admit that currently we are not very good at it. So we need to improve the way that stability studies are designed, but also the way that stability studies are reported. What is wrong with the design of stability studies? Well, if you think about the factors that I've mentioned in the very beginning of my presentation, all factors that may affect the stability of an analyte, then we can come to a long list of potential sources of variations in the study design. And if the authors have not standardized, if these factors are not standardized, and I mean all pre-analytical factors, but also analytical factors, if they are not standardized, and if there is a lot of heterogeneity in those factors, then also there will be a lot of differences in the results that these studies produce. And those potential sources of variations are many. The tube type, the sample matrix, the patient population, the way the sample has been collected, mixed, transported, the way temperature has been measured, etc., etc., all the way to the the analytical phase, you know, which method have you used, which instrument did you use, did you test your samples in batches, you know, the traceability issues, calibration, did you, how many replicates did you do, did you spike your samples, etc., etc. So there are a number of potential sources of variations. And exactly because of this, we have a huge variations in the differences in between different studies. And this is nicely illustrated by Ruben Rioja and his colleagues in a study published 2 years ago. And he gave a couple of analyses and showed that different studies published by different authors produce very, very different results. So here is an example for glucose. And here are the results for the stability of glucose if the sample has been refrigerated. This is the left panel. And the right panel is the stability of glucose at room temperature. The upper panel is for the stability of glucose in serum and plasma, and the lower panel is the stability of glucose in whole blood. And let's just look at the stability of glucose in whole blood. Look at the differences in stability or deviations. Here is the percent deviation. Look at the differences that come from different authors, and all those differences are because or due to differences in the study design and variations of all those factors that can affect the stability. Same thing with phosphorus. Look at the stability of phosphorus at room temperature in whole blood. Look at the differences in deviations. And the same with potassium in whole blood at room temperature. Look at the deviation. So obviously there is a room for improvement, and this has been recognized by many colleagues and also by industry. This is up until very recently, actually, there were no standards for really designing the stability study. And this was nicely illustrated by these authors in a recently published paper. And the authors actually say that guidelines for laboratories and manufacturers from the Federal Registry in the United States are not prescriptive and allow too much flexibility to suit the individual needs of the laboratories and manufacturers. And they also conclude that the literature is lacking quality data on how best to perform this analysis. And this has been nicely addressed by Spanish Society of Laboratory Medicine and their working group on Extra Analytical Quality Commission, chaired by, again, my dear colleague Ruben Gomez Rioja. They have last year published a very nice paper, a protocol for testing the stability of biochemical analytes, which offers a detailed guidance on how to properly design a stability study protocol and control all potential sources of variations. And I recommend to all of you who plan to do a stability study to read this document carefully and to follow the suggested procedure to design a stability study. Okay, and the last thing that I wish to address in the remaining couple of minutes of my talk is the way that stability studies are reported. Why do we need standards for reporting stability studies? Well, because the reporting is currently really not satisfactory. The way that stability studies are reported at the moment is not standardized and not transparent. So actually a lot of essential information is missing. So maybe authors have done a nice study and have done it in a very nice way, but they have failed to report all essential information for the readers. And this actually makes very questionable study applicability, study transferability, study reproducibility, and replicability of study results and conclusions. And to address this issue, the EFLM working group for pre-analytical phase has published very recently actually a checklist, a CRESS checklist for reporting stability studies. We actually hope that by adhering to this checklist, the authors will ensure that the study is reported in a transparent way, and if reported in this way, it will be easily replicated. The checklist has 20 items, and it goes from the title and keywords, and then follows all essential parts of the manuscript. Just for example, as an illustration, it actually reminds you to mention all what is important under the different sections of the manuscript, to ensure transparency and reproducibility. So it asks you from the very beginning to clearly indicate in the title that, for example, the content is a stability study. So in that way, the authors who are interested in the stability of the analyte that you have studied will easily identify your study if doing a PubMed search, etc., etc. So I don't have much time to go into details, but definitely I recommend it to everyone who has done a stability study and is now about to publish it, to go through the checklist, follow the checklist, and make sure that all these important aspects are covered. Our desire is that researchers and authors will use the CREST checklist as a guide to produce standardized reporting of future stability studies. We also encourage reviewers and journal editors to use the CREST checklist as a guide to assess and evaluate the way stability studies are reported. And finally, we encourage all readers to look for important details and pieces of information listed in the CREST checklist when reading stability studies. We hope that our checklist will improve reporting of stability studies in the future. So going back to challenges, by these two standards, we hope that those challenges are successfully addressed. Nevertheless, there is one challenge still that remains to be addressed, and this is the question of how to assess the quality of stability studies. And we in our working group have already started to do some work in that area, and we hope to have some interesting stuff coming out soon. To summarize, the take-home message from this lecture would be that analyte stability is extremely important for defining whether the sample is appropriate or not for the analysis. At the moment, we don't have enough evidence to make an informed decision on stability specifications. So obviously there is a need for improvement. The assay declarations need to be improved, but also we need to improve the way that we perform stability studies. And luckily, standards for design and reporting are available. So whoever is planning to do a stability study and then report it, I warmly recommend that you follow the available standard and make sure that you comply with their recommendations. Thank you.